Does anyone want to ask a question about the quiz? Anything? We're okay? All right. What I'd like everybody to do is take out a blank piece of paper. Pardon? No, you're not going to be turning it in, so if you have plain paper rather than line, that works even better, but if you don't, the line will work. Okay? Have you got a straight edge? Anything will work. What I'd like you to do is find something that's about an inch or 3/4 of an inch or something wide, and put it on your piece of paper, and just so that you don't get mixed up with your lines that are already there, for those of you who have lined paper, kind of put it at an angle, and then draw in a line on each side of your straight edge. If you don't have one, borrow one from your neighbor. Okay? Then, once you've drawn your two sides, just any way you want. Let's try to avoid a 90-degree angle to those two lines. Draw in a transversal. Okay? Now what I'd like you to do is, with a protractor, either the one I gave you or another one, I would like you to measure all of these angles that we created when we cut the two lines by a transversal. If you did what I asked you, the two lines should be what? Parallel, right? Okay? Question. Do the two lines have to be parallel in order for this to be called a transversal? No. If you were able to open that GeoGebra file, did everybody get it open and you were able to check the little check boxes to have it identify the different, yes? Okay. So I could have a line like this, and I could have another line like this, and that could be a transversal, right? Transversal, the definition is a line that cuts two or more other lines. But in our case, we've got it so that they are parallel. Would you please, how many different angles are there when two lines are cut by a transversal? Total angles? Huh? 8? Okay, 4 at each intersection point, right? Measure them all, get their measurement with your protractor, and just write in the size.
Oh, correspondent.
Corresponding angles? What else? You kind of put two together. Alternate interior.
And then alternate exterior.
So that's the ulterior. There we go. You're thinking of an ulterior motive. And what other one? Alternate. Exterior angles. Any more? The transversal that cuts them. Okay, that's not an angle, but that helped us to get the angles. There was another pair there that we gave you.
Consecutive interior angles.
Okay. Consecutive interior angles. vertical angles. Every one of these always come in pairs. You can't say here is a alternate interior angle. There's no such thing. It has to be this pair. As a pair are alternate interior angles. This as a pair are vertical angles. You cannot have one vertical angle because these names name relationships by pairs. If I were to number those 8 angles that we just measured, someone give me a pair of corresponding angles from this diagram. Did you do this, Suzanne? You what? Are we guessing? Did you guys do this?
4, 8, 1, and 5,
Yes?
3, and 7.
No?
You have 2 and 6, 4 and 8, 1 and 5, 3, 7, right?
We better get people in here and so here was the app that you were given, right? So did everybody figure this out? See the little check box right there, and it says ABH and DCB. And notice, ABH and DCB are highlighted, and it gives their measurement. If I check these other corresponding pair of corresponding angles, so I turn that one off, it moves. They're all, how about that? There's another pair of corresponding. Okay? There's another pair of corresponding. There's another pair of corresponding. So, did you define a corresponding angle? What was your definition? This should be in your glossary right now. What? Measure? 144, 153.45? Aubrey?
I can't remember exactly what mine said, but I think I said something about it being on the same side of the transverse line.
Okay, I think we could include that in our definition. They are always on the same side of the transversal. But if we just stop there, I could say those two, right? Or those two.
And on the same, like, if you were to say that B and C were the center of a quadrant, that they would be in the same quadrant? Like they're both in the bottom right-hand side of point of the triangle?
I follow what you're saying.
But maybe just in different terminology.
Well, I'm saying, could a 5th grader understand this? Your definition.
If you were to make B be 0, 0 on a grid, and C be 0, 0 on another grid, they'd both be the corresponding triangles, or the corresponding angles would be in the same quadrant on a graph.
I follow what you're saying there now. Now you'd have to teach them about quadrants. Okay, so you're using something you know. Okay.
So would you say it's the same side of the transversal and the same side of the other 2 lines? Like on the same line?
Meaning as either both above or both below.
Yeah.
Okay, now I think we're getting, 5th grader would probably be able to follow that. Right? Okay.
I just use a definition of they're in the same corner. Students might not understand that concept better than quadrant.
The angle,
Yeah.
corner. quadrant. But what does same corner mean?
You know, the transverse line. And assign each point, 4 corners.
Okay, so each of these, then we get assigned 4 corners. It's in the same,
Corner.
it's in the same corresponding area. Hey, what are we calling these? Corresponding. Maybe this is where the name came from. Because their position corresponds, you know, as she was saying, both below, both on the same side of the transversal, both above, both on the same. So somebody give me another, or somebody give me a pair of corresponding over here. 1 and 5, 2 and 6, 4 and 8,
3 and 7.
and 3 and 7. There's actually, okay. See how this works? All right. How do you remember, how are you going to remember these? By the way, I could have given you definitions, right? Handed you definitions and say, memorize these. This is a little bit different way to teach vocabulary. Was it effective? Was it helpful? Does it? I think it gets students. Have you ever had to do a vocabulary assignment? What does the teacher do? Give you the words and write out the definitions, right? Sometimes write them out 4 times so you learn them, right? Did you enjoy that?
Not even a little bit.
I'm trying to model, what other ways have we given you to learn definitions in this class so far?
I really like how you show an example of it and we need to come up with a definition ourselves because we're stretching our minds and we're trying to understand it before we even know what the definition is.
I gave you examples
And then you showed us what it wasn't.
and non-examples. Why did I give you the non-examples?
So we wouldn't come up with our own ideas kind of thing and be like, oh, that doesn't work.
Your definition for the one that was the example can't fit the one that's not. If it does, you haven't got a very good definition, right? Does everybody see what I'm... That teaches students discriminating skills and those kinds of things. So, okay. Well, I'm just worried. I look out here and I get this glazed look like... Because I'm asking these and not everybody's with me and you need to have been there. You need to have your definitions written. Because now the question I want to ask is, are any of these pairs ever congruent? As a pair. So is a pair of corresponding angles ever congruent? And that's what you started out saying, and I said, well look, here's a pair that's not.
Yeah, so like if the lines are parallel,
Oh.
that's like
What did you find as you did your parallel line? Are your pairs of corresponding angles congruent? So as a pair, we would say that these are congruent. When? Only when the lines are parallel, right? Anything else you found besides the corresponding? Yes.
Like regarding this?
Yeah.
Oh, okay. So if you just looked at one of the lines, the one angle, like for me it was 15 and the other one was 130, so the line is going to equal 180.
Oh, so so what word, have we given you that word yet? 50 and 130, supplementary. They add up to 180. By the way, get something that you've got in your head already and hook this onto. When we say alternate interior, we're talking about alternate sides of the transversal and interior. They have to be inside. So there's a pair of alternate interior. It says what it is. Alternate exterior would be on alternate sides, but on the outside. So this would be a pair of alternate exterior. They're on alternate sides of the transversal, and they are on the exterior of the two lines. That's where the names are coming from, right? Okay. You found that some of them were supplementary if they were side by side. So like number 1 and 2, and 2 and 4, and 3 and 4, and 1 and 3, and so on, right?
Yeah.
Okay. Anybody find any other congruence in any of these pairs? Yes? No? What? Oh.
The vertical angles should be congruent with one another, like they have the same values.
Vertical angles.
So like 2 and 3
2 and 3 should.
1 and 4 should.
1 and 4.
5 and 8, and 6 and 7.
Is that true only when the lines are parallel?
No.
That's true all the time, right? Okay? So this one's always congruent. These are congruent for parallel lines. How about any of these others? Yes? No? Look at your measurements. Find a pair of alternate interior. Yes? No? Huh? 3 and 6. Look at your 3 and 6. Are they the same size?
Yes, but it could go to parallel lines.
Because the lines are parallel.
That one wouldn't be.
This one would, that 3 and that 6 wouldn't be, you're saying. Okay? And you can tell because one's a obtuse and one's acute. And how could an obtuse be equal to an acute, right? Okay? So these are congruent when the lines are parallel.
Why isn't there a consecutive exterior angle that we look at?
What do we mean by consecutive?
I took it to mean on the same side as the transversal.
What does the word consecutive mean in, if we say consecutive numbers, what does that mean? One right after another. Consecutive presidents of the church. One right after the other, right? So maybe it's because if they're on the outside, they're not right next one after the other. Okay, good question. How about consecutive interiors? Are they congruent as a pair? Give me a pair that's consecutive interior.
4 and 6.
4 and 6. And 3 and 5. Check your positions of 4 and 6, 3 and 5 with your parallel lines. Are they? They're what? They're supplementary, not congruent, right? Okay? So when the lines are parallel, these add up to 180. How about these? What'd you find as a pair? That would be like 1 and 8, right? What's your 1 and 8 like? Your 2 and 7? Congruent? If the lines are parallel, right? So here's 1, 2, 3. 3 of these are congruent when the lines are parallel. 1 always is. They don't have to be parallel. And these aren't congruent, but they're supplementary. They add up to 180 together. Maybe I ought to use that word instead of 180. Supplementary. Okay. Question?
Just so I get this right, so an alternate interior would be like 3 and 6?
Yep. Yep. Okay. The other day we took a look at the sum of the interior angle of a triangle. We did that by drawing out our own triangles, measuring the 3, adding them up, writing it on the board, and they almost all came to 180, and those that weren't were very close, and we decided that depending on how you rounded your measurement, that may account for the error. Then what did we do? No one was in. Come on. What? You guys all just eat lunch and you're having sleep, or you tore off the corners and what? Put the vertices together, and everybody's formed a straight line which we knew contained 180 degrees. Then what did we do? Then I went to the technology and I drew a triangle and we measured the three angles and we added them up. And we dragged it around and we saw that all of the ones we looked at all added up to 180. And then I asked what? Does that prove that all triangles add up to 180? And all of you, yeah. But all it takes is one counterexample. You cannot prove anything by looking at even 1,000,000 examples. Now, if you've looked at 1,000,000 examples and it's been true for all 1,000,000, you're probably feeling pretty confident. In other words, the strength of our argument is probably pretty sound, but don't lay your money down. Because all it takes is one non-example of that happening. And so what I want to talk to you about is how can we prove that all triangles, no matter what we did? I'd like to illustrate that with a deductive proof rather than an inductive. We're not looking at specific examples and saying, well, every time we looked at it, that's the way it was. And we're going to say, okay, so I'm going to draw a triangle here. And we're going to prove that the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3 is 180, so that no matter what triangle we look at, that will be true. Here's how I'm going to do it. I'm going to do it by drawing in an auxiliary line right here, such that that line and this line are parallel to each other. By the way, these little arrows on them indicate that's the symbol for parallel. All right? And then for our purposes, I'm going to put in a 4 and a 5 up here to represent this angle and this angle. All right. Would everyone agree with me that the measure of angle 4 plus the measure of angle 1 plus the measure of angle 5 is equal to 180? Why? Because it makes a straight line. And if we understand that a straight line is 180, we've got to accept this statement, right? If we can all accept this statement here, we'll move on. Would everyone agree that the measure of angle 5 is equal to the measure of angle 3? Yes? No? What? I said I just drew a line that was parallel, so what? So when two lines are parallel, are cut by a transversal, then what? What are these? Alternate interior angles have to be congruent. That's what we just discovered, right? And we could also say the measure of angle 4 is equal to the measure of angle 2 for the very same reason. Here we've got two lines cut by this transversal, and those are what? As a pair? Alternate interior angles. Okay? So over here, there's 180 degrees on a straight line. That's why this is true. This is true because alternate interior angles are congruent when the lines are parallel, right?
Right.
Okay. So now I can say then the measure of angle 2 plus the measure of angle 1 plus the measure of angle 3 is equal to 180. How can I say that?
By substitution.
Where did I substitute? And what did I substitute?
2 and 4.
Since 5 and 3 are the same, up here where there's a 5, I can take the 5 out and put the 3 in, and I will get the same result because they're the same. Up here where there's a 4, I can take the 4 out and put a 2 in because 2 and 4 are the same, and I end up with this, which tells me that the angle 1 plus 2 plus 3 is equal to 180. And guess what we've proven? That in a triangle, the sum of the interior angles add up to 180. And now we know we will never find a triangle that doesn't add up to 180 degrees unless we go to a different kind of geometry. Lauren goes, whoa, wait a minute. Let me just illustrate one. This is a joke you may have read, or a riddle that you may have read. A hunter walks 5 miles straight south, shoots a bear at this point, then he walks 5 miles straight west, then he walks 5 miles straight north, and finds himself back at the same place he started. What color is the bear? Huh?
Didn't you say what the color of the bear was in the riddle? And you just give
Did
it-
I? I said shot a bear. Didn't I?
I thought you said you shot a brown bear.
I didn't. Yeah. How do you know? How do you know?
Because it's the only place that you can make 3 right angles.
I just made a triangle with 3 right angles. I'm at the North Pole, I go straight south. I turn and go west, that's what degree? 90 degrees for 5 miles. Then I turn and go north. Have you seen a globe? I go straight north, I end up back where I'm at. There is a triangle that has 3, it's an equilateral triangle. It has 3 right angles in it. It doesn't add up to 180. Why not? We just proved that they did. Because it's on a sphere. And this is on a flat surface, what we just proved, right? And so it takes us to a different geometry. Don't worry about that. We're not going to go there. I just threw that out there to show you that we've got to understand where we're at and what we're doing. And this is in Euclidean geometry, and they will all have 180 degrees. Okay. Now.
That was so mean.
Huh? What?
That was so mean.
What was mean?
It's like, this is Euclidean geometry. That's non-Euclidean geometry. It's like, that's hilarious. That's mean.
Okay. Well, we've got to let you know that there are some geometries that we're not going to be learning about this year, this semester. Okay? All right. We need to do this. If you've got your laptops, pull them up, and let's. We're going to do some investigations. Pick your favorite number anywhere from 4 to 12. So pick your favorite number from 4 to 12. When you do it, after you've got your number picked, would everyone please indicate what number they have chosen by holding up the correct number of fingers? If you're 11 or 12, you might, I don't know, hold it up like this so that there's, I don't know. But just give me an indication. I want to see what you've chosen so that we've got a good representative. It's got to be a number 4 to 12. You could include 4 or 12. Okay, this is going to work. All right, so what I want you to do now is with your program here, what I'd like you to do is get a new, so if you've got GeoGebra up, just Control N, brings up a new window, or just start it up. Get rid of your grid here. And then the one we want to go to is regular polygon. Okay? We're going to build right now no, we don't even have to do a regular. Let's do one that's just polygon. We'll go polygon. So if my favorite number was 6, what I would do is this: 1, 2, 3, 4, 5, 6, and then I'm going to close it up by going to the original. And I just created myself a 6-sided polygon. What's the name of it, by the way? 6-sided hexagon. Okay? All right? Now, who had a 6? Did anybody have a 6 in here? 3 of you? 4 of you? Well, yeah, I'll do this just to... Now what I want to do is I want to find out how big each of these angles are. So what do? Come up to the angle measurement tool. Right here, and it says select 3 points or 2 sides. Now you remember you have to do them in a certain order, right? Or it'll do the reflex angle, it'll do the one outside instead of inside.
Just go counterclockwise.
So counterclockwise, so if I want A, I'll do B, A, oh. That's the wrong one, right? Control Z, let's oh, it undid everything. 6 here.
You can do it with polygon you want.
Let's see, we can do it by doing side lengths, right? Or by sides. So let's just do this here and here. Ah.
You have to go like A to B. You have to go
Clockwise. Don't go counterclockwise. Go clockwise.
There we go. Here. Here. There we go. Here. 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 There. 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 And measure all of your angles. Go ahead and be doing this for your number of sides. If you have a 12-sided, do a 12. Okay? And you'll notice over here that these numbers are, let's see, I've got 1, 2, 3, 4, 5, 6. I've got that 7th one that I really don't want, right? Okay? So, what I'm interested in is what these all add up to. So, do you remember how to do that? Down here on the input line, I go down and click on it. And I want to add beta, the first one right here. So I click right here and say beta plus, and I want to do gamma plus, I'm going to add them all up. Right here, just go around and plus, 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 and finally,
I got distracted because that
It's
one
okay.
was
Take
like
it.
I could have put it out.
and I hit enter, and it just gave me the sum as being, is that right? I got 360. That can't be right.
Yeah.
What's going on? Let me click to see if that's, if I write.
Oh, I know, squash a lot.
1, 2, 3, 4, 5, 6.
What did I check? Because the triangle.
I did it all and then it went
Quadrilateral.
That's wrong.
I think
Is that
it's negatives.
Yeah.
Huh.
Maybe you added. I think you forgot your alpha.
I did forget my alpha, but I didn't want my alpha because alpha is out here. And that, I don't want to add that one up. I just want to add the beta and the gamma and the. So that's what I did, right? 1, 2, 3, 4, 5. I did my 6 interior angles. What is going on? Well, maybe this isn't going to work like I was hoping.
Maybe you found an exception to the rule.
Huh?
Oh, joking.
I should have gotten 720. So, did anybody have four-sided? What was your total? 360. 4-sided? Anybody? 360. How about 5? What'd you get? 180.
Yeah.
When you added the 5 together, you got 180 on a 5? You got 180 on a 7. Well, we're going to have to figure out what is going on here.
I think what's going
I
on.
don't think it's going to make any difference. We could. Let's do it with regular. Go to your regular one and build a regular one just off to the side. Does everybody know how to do that? And what we're going to do is, to build my regular one, I'll come out here and go 1, 2, and then it tells you how many, and I want 6. So you enter it, and there it is. Okay. Did everybody see what I did? You click on this little thing, and you can grab it and move it around. Now just do one angle. We're going to trick it. We're going to trick it. Okay. And so that angle, on a regular one, they'll all be the same. So in order to get my total, what I'm going to do is I'm going to come down here on the input and say, get that angle, which is that one, and multiply it by 6, because there's 6 of them, and hit enter. Whoa! Now I'm really blown away. Because, can everybody see? That is not, wait a minute. That is 120, and if I go 120 times 6, I don't get 360.
I think the reason it's doing that is because there's only 360 degrees in the circle that it starts over.
Shouldn't matter where. 120 times 6, you saw me, right? Right here. There it is. Take, I put a times in between. Definition times.
But the more you add, more sides you add, the bigger your angle becomes.
Measure 1, grab your calculator, multiply by how many sides you had. We'll get there. Oh my goodness. Can you tell I'm teaching this class with GeoGebra for the first time?
I went into the preferences of what it looks at. It will only go up to 360 because once you hit that, you're at the beginning of the circle, and it will start going again from 1. So if you do like 70 plus 70, it'll give you 140. But if you get it so that it's high enough to
Oh,
360.
I see. That's what it's doing. Because okay. Did everybody hear what I, measure one, take that amount, take your calculator, don't let this do it, because it's doing something strange. Give me the total. We know 3 is the number of sides
Plus this one, they gave me
and the sum
90.
of the interior angles.
Starting.
We learned last
And it goes back to
Tuesday there was 180, right? Who had 4? When you took your angle and multiplied it by 4, what did you get?
360.
360. 5, you Pentagon people. 540, well, 540 when you did this, okay. So, yes, you've caught on to what it is. What they do is they add them up, it's 540, but that's 180 past the 360, so it was kicking out 180. So what it does is you up? For what? For 6. What did you get for your angle? When you measured one angle of the regular.
Oh, regular, it was 720.
720 for all of them.
Yeah.
Each one was 120 and there were 6 of them, so that's 720. You with me? Anybody have a 7-sided? Who's lucky number 7? Yes.
900,
What'd you get?
900.
900.
They go in intervals of 180 degrees.
Anybody have an 8? Octagons? Yes.
1080.
9? Anybody have a 9-sided one?
Should be 1260.
Nonagon? Nobody did it. Nobody's lucky number is 9? I should have done that one.
It's
That's how many
1260.
kids I ended up with. What is it?
1260.
1260. 10.
1440.
1440. Anybody do 11 or 12? Nobody did 11 or 12?
1620.
On 11 or 12? 11 is 16, 20, and 12? What? 18. Okay. Now, what if I had n sides?
10 times 180.
Well, that would
Or
be
N sides.
times 1 is
Sorry, minus 2.
and minus 2
N minus 2.
times 180.
So if you took 3 minus 2, you get 1. 1 times 180 is 180. 4 minus 2. Why is that the formula? Can everybody see that? If I were to take 6, 6 minus 2 is 4. 4 times 180 makes 720, right? Let's give you a visual illustration about how this might be the formula. Are you ready? In a 4-sided figure, if I draw in all the diagonals I can from one vertex, that's it. How many triangles were formed? 2. How much does this triangle have as the interior added up, all 3 angles? 180. How about this one? So 1 plus 2 plus 3 would be 180, and 4 plus 5 plus 6 would be 180, right? But you'll notice that this angle of the quadrilateral is made up of 3 and 5, and this angle of the quadrilateral is made up of 1 and 4. So if I add 1, 2, 3, 5, 6, and 4, I should get the total number, right? Well, that's just 280s, right? So when I had 4-sided, I took 2 times 180, because there were 2 triangles in there. You with me? A pentagon, on the other hand, if I draw in all the diagonals I can from one vertex. I'll pick this vertex. I can draw in that diagonal and that one. That forms how many triangles? 3 triangles. They're each 180, right? And 1 plus 2 plus 3 is 180. And 4 plus 5 plus 6 is 180. And 7 plus 8 plus 9 is 180. And 5 and 9 make up that one, and 3 and 4 make up that, and 1 and 6 and 7 make up that. So if I add the angles 1 through 9, I should get my total, right? Well, that's just like saying 3 times 180, because each, does that make sense? 3 times 180 when I have 5, right? Moving to a hexagon. Drawing in all the diagonals I can from one vertex, I get how many triangles? 4. Each of them add up to 180, so my formula for 6-sided is 4 times 180. So what does this 2x or n minus 2 stand for here?
There's always 2 angles that you like counting. Like 2 and 8, like on the 5-sided one. There's 2 angles that aren't even counted. Like
I'm counting them.
okay.
I'm going to add those in.
Well, one line doesn't make an angle. You have to have 2 lines to make an angle. Does that make any sense?
I don't know what that means with respect to this.
I'm trying to. So, because you need 2 lines to make an angle, you.
2 raised to,
Yeah.
okay.
I can't explain it to that. It makes sense in my head, but I don't know how.
Yeah.
You can't pick the 2 angles that are connect or next to it. So you can't pick 2 consecutive angles. So that takes away those 2.
Ah,
If
so
that makes
this
any
angle
sense.
cuts this
And
side,
you
this
can't
angle cuts that
connect
one,
those.
but these 2 sides don't get cut by an angle, and therefore there's 2 less. Okay, is that what you're going to say, or?
Pretty much.
And basically all I'll say is this: if you take any polygon and draw in all of the diagonals from one vertex, you will always get 2 less triangles than there are number of sides. And that's the reason why, right? That's why this formula could work, correct? Let me give you a different viewpoint. What if I were to tell you that this isn't the formula for finding the sum? What if I were to tell you it's a different formula? Let me give it to you. If I were to take a 4-sided figure and put a point on the inside and draw in segments connecting the point to all of my vertices, how many triangles have I produced? 4. Each of them have 180, so if I go 4 times 180, that'll give me the sum of all the interior angles of the quadrilateral, right? Yes?
No, because you're also including.
You're including the 360 in the middle.
Oh, there's these angles up here, these 4, that aren't part of my interior angle sum, right? And how many degrees are there? So if I subtracted 360 from this, that should give me the answer, correct? Check it out and see if it doesn't give us the same thing we got 360 over here. Do the math. Let's do a pentagon. Put a point anywhere in the middle. Connect all of the vertices. How many triangles will be formed? 5. Each one of them measure how much when they're interior sum? 180. So that should give me the total, right? No. I've got these angles in here that aren't part of my interior measure. And how much is that? So if I took 360 away from that, I would get the right. Let's just check it out. What is 5 times 180? 900, right? Minus 360 is 540. We're getting the same thing.
Well, isn't that the same thing? Because if you did So n minus 2 times 180. So if you took the minus 2 out, it's n times 180 minus 2 times 180.
Using this formula, if I were to have an n-sided polygon, what would I write?
It would be like n times 180.
N times 180. Each one of them
Minus-
have 180 degrees in them.
Minus 2 times 180 or 360.
Minus the full circle or 360 of the ones. We don't know how many there are. There are n of those angles, but they will all add up to 360, and I subtract that out. So tell me, which formula is it? This one? Or this one?
They're the same.
They're the
They're
same?
the same, just written differently.
It's just, if you reduce that one.
Reduce it? Distribute it? If I went 180 times n and then 180 times 2, I would get that. Or over here, if I factored out a 180, what would be left over? An n minus a 2, right? They're the same formula. But can you see that where the formula comes from is different?
Yeah.
Okay? I will guarantee that I will ask you on your exam, I will ask you to find the sum of an interior angles of a polygon. Then I'll ask you, how did you do it? And then I'll ask you where your formula came from. If you choose this formula, this should be the explanation, right? That 360 around the middle of every one of those has to be subtracted out. If you use this formula, I would expect this kind of an explanation. Does that make sense? I think it's helpful to know both. We've run out of time. We're having so much fun. At least we know what GeoGebra's doing now. Now I've got to figure out how to make it so that it turns, you can change that setting. Anyhow, tonight, for part of your assignment, or not for tonight, but next Tuesday, you're going to discover this right here is what? We didn't write it down. What is this? The formula to give us the sum of the interior angle of an n-sided polygon. Tonight you're going to inspect, or you're going to investigate what is the sum of the exterior angles of the polygon. Does everybody know what an exterior angle is? This is not it. That is not an exterior angle. Have we given you that definition in one of your things yet? Exterior angle? Yeah? It's when you extend a side, that is an exterior angle. Right? We've seen this? Okay. That's what you're going to be doing. One of the things you're going to be doing.